Hi, today we're talking about isoelectric points of amino acids and proteins. Let's go. So, amino acids have two functional groups. One of them is amino group, right here, and the other one is carboxyl group, right here. Together, amino acids, carboxyl from carboxyl acids, that's why amino acids. Now, what's interesting, these two groups will behave differently in different conditions, different environment. And here, what's the most important is the pH. Okay, so let's take a look at that. We'll start from the balanced form, which is Zwitterion. Why is it balanced? Well, we can say that one group, the amino group, has positive charge in here, and the carboxyl group has negative charge right here. So together they balance each other, and the overall charge, or net charge, if you will, of this amino acid is 0. So remember, 0 is for Zwitterion. So let's take a look what happens to the Zwitterion if we change the pH. So let's say we go a bit lower. Now lower pH means that we have a lot of H pluses, right? A lot of H pluses are high, and because of that, some of those H pluses from the environment will bind to this carboxyl group that is negative charge. Remember, negative charge in here, positive on the hydrogen, they will attract each other, and as a result, we'll have OH group. Okay, so this hydrogen will combine with our carboxyl group, and we have all the functional groups are protonated, if you will. Now, what is important, this process is kind of an equilibrium. Okay, so it goes in both directions. So it's not like all of the amino acids will have this form. There will be some balance. We can say there will be some constant, and constant K. If we have some constant, we can have pK. Let's call it pKa1. Okay, so we have pKa constant for this reaction. We'll use it in a sec. Now, let's take a look at the other side. So what happens if you have higher pH? Higher pH means basically that we have our H pluses are lower, right? You can also think that OHs are high. So H pluses are low, OHs are high. What happens? Because there are, let's say, a lot of OHs in the environment, this H plus from the nitrogen will be taken away, right? Will be taken away to this OH, for example, forming water, or in any way it will be just out of this amino acids. So what will be the result? As a result, we'll remove this hydrogen from here. So when we remove this OH plus, our ion has negative charge in here. That's also an important thing. So previously, here, the only charge left was positive. Okay, I can say it's positive. Here, it's negative. And similarly as before, we'll also have this equilibrium. Let's write it down. And also some K, so also pK. pK value, let's call it pKa2, for example. And now, you might get asked, okay, what's the isoelectric point, or what's pI? So basically, what's the pH at which our amino acid will be in the form of Zwitterion? So charge 0. Remember, it's all about the charge. So Zwitterion, charge 0, what is the pH? So it's important to take a look at the pKs close to our Zwitterion. So it might happen that you have more forms, because you will have more functional groups, for example, from the side chain. So what's important is to take two neighbors, okay, neighbors of the Zwitterion, and the pI for the Zwitterion will be basically the average of those, okay? So it will be pKa1 plus pKa2 over 2. Oh, that's a bad one. Okay, so now you'll be usually given some values. Let's say this is 2, let's say this is, I don't know, 8. Okay, they will be given to you, might be different. You just plug them in, divide, and you get the answer. Okay, so the pI for your Zwitterion, for your amino acid, is in this case 5. So it means that at pH 5, most of your amino acid will be in this form. Now, what happens when our side chain, it's not like any side chain, but it has one of these two functional groups. Let's say we'll have something like this, COOH. Okay, so another carboxyl group, it's some acid. So let's take a look. Let's make a scale with the pH again. Now, in order to figure out how does our amino acid look like in specific pH, we'll need the pKa's values for each of the functional groups. So let's say that this group will have pKa, let's say 2. This one will have pKa, let's say 4. And this one will have, again, pKa 3, and it will be 8. Okay, they will be given to you usually in a question or in a text or in some way. So now, when pH is below the lowest pKa, it means that all of them are protonated. Okay, all the functional groups have some additional protons, or as many protons as possible. So either carboxyl is just COOH, and amino group will be NH3+. So pH is so low and there is so many hydrogens that everything is protonated. So as all of them should be protonated, our amino group will also be NH3. Okay, you can have this as a full structure or just NH3, something like this. It's the same. Now let's take a look at the charge of this amino acid. So, well, here it's a positive. Okay, it's plus 1 because this hydrogen here came from the environment, and now the overall charge would be plus 1. Now let's take a look a bit further. So what happens if we go above our first pKa? So let's say that's our pKa. Okay, some equilibrium. Now what next? So further, as we go above this pKa, this first pKa, this hydrogen will dissociate, will be taken away from our amino acid. So let's draw it. Our carboxyl group will lose its hydrogen, and we'll have just negative charge left in here. So hydrogen was taken away from our amino acid. Now, when you take a look at this, you have both negative charge and positive charge, right? The rest one is neutral. This is 0. So overall, they balance each other, right? And when we have everything balanced, overall charge would be 0. That's Zwitterion. Okay, so that will be the form of our interest if we're about to calculate the pi. But let's take a look further. What happens if we go in further? So the next higher pKa would be this one. So pKa 2, it's 4. Let's take a look. So we make this equilibrium, pKa 2, which is 4. In this case, 4. So what happens to our amino acid? Let's take a look. Let's copy this one. So as we go above the pKa 2 of specifically for this functional group will lose its hydrogen. Okay, so this hydrogen again will be taken to the environment, will bind with some other ion or something will happen to this hydrogen, and we are left with additional negative charge. So now this charge is neutralized with this one, but this one is kind of negative, it's extra. So overall it will be negative 1 net charge, overall charge. So what happens further? Let's say we go even further with our pH above the third pKa. So let's take a look. We go above pKa 3, in this case 8. So in this case, all of these carboxyl group already have already lost its hydrogen. Now it's time for the amino group. So the same will happen to this group. This hydrogen again will be taken to the environment, and we are left with something like this. Now there is no positive charge on this nitrogen to balance any of the on the negative charges on the carboxyl groups. So the overall charge will be negative 2. Okay, that's the thing. So it always increases by 1 with NF, and with extra hydrogen you'll get 1. If you lose hydrogen, you'll lose 1. So from positive 1, 0, negative 1, and negative 2. Now let's say what is pi. So you'll be given 3 pKa's or even more, but what's important is the one closest to the Zwitterion, so the neighbors. In this case, pKa1 and pKa2, these two guys. So we'll do it the exactly same way as we did before. we'll just take the average of these two. Let's take a look. In this case, pKa1 plus pKa2 over 2. So that would be 2 plus 4 over 2, 3. So at pH 3, our amino acid will be the most abundant in the form of Zwitterion. Now, what happens if we have some proteins, so multiple amino acids connected together? How to figure out the PI in this case? Let's take a look. Let's say we have tripeptide like that. We have 1, 2, 3 amino acids. Okay, green, black, and blue. So we have to take a look at our functional groups that are important. So NH2 group at the very beginning and COH at the very end. Beside that, you have to check if your side chains don't have any functional groups. So in this case, I see COH and NH2. So you should be given pKa values for each of them. It's kind of similar as we did in here. And you could actually do it the same way. So you just take a look, make a drawing, make a scale, figure out which form has the zero charge, what's the Zwitterion, take the neighboring pKa values, take the average, that's it. Voila, you're done. But you might be given a table like that. So let's take a look what's in the table. So the table gives you pKa values for each and every functional group. Let's actually write down these pKa values corresponding to functional groups. So COH group, if it's not in the R, it means that it's just the terminal one. So that would be this pKa 1.8. Now NH3, the same, terminal. pKa 2, 7.8. Next, NH3R group, pKa 3, this one. And this is 10. And finally, COHR, so pKa 3 by 3, it should be 4, so it's 4.2. Now, when you take a look at these, you can see that the change in the charge, take a look, these columns here represent the charge of a given functional group, will change closely or at the pKa value. So if that's 1.8, when you go a bit farther, well, actually, it's like this one should be -1. So when you go farther than 1.8, so for example 2, you should get -1. And since then, it will stay -1. You see, it's the -1 till the very, very bottom, which makes sense. If you go with the pH even higher, you have even less H pluses in the environment, so your functional group COH will dissociate, will give you H's to the environment. So you have negative. Okay, cool. How to figure out where is the Zwitterion, how to find the PI of this protein. So we need to take a look at the net charge. Okay, net charge. So that's what we calculated in here, these numbers, right? But here, instead of kind of doing it manually, we got a table. So we remember that Zwitterion is for net charge equals 0. When net charge is 0, then that's the Zwitterion. So we'll pay special attention to these rows of the column. Okay, that's the thing. Here is the border. So in order to figure out which two pKa values are important for us, we need to see which functional group changes its charge at this border. So for example, COH, it doesn't change its value, right? It was -1, negative, doesn't change anything. But NH3 does change. For example, okay, positive, but here, border, and it changed. Okay, you see this change in value from +1 to -1. Okay, the rest was the same, right? The same. Here, it changed. So we have one pKa value that we'll need. Let's try to find another one. Okay, how about this one? Well, it's the same. Here is our pKa value that is important because, again, the value changed. You see, it means that it either gained or lost some hydrogen group, which will affect whether we have Zwitterion or not. So we have these two functional groups and also corresponding pKa values. So our PI would be, again, in this case, pKa2 plus pKa4 over 2. 7.8 plus 4.2 over 2, which is 6. Okay, so at pH 6, our amino acid will be in the Zwitterion or will have net charge of 0. And that's it. That's it for today. If you have some questions, let me know in the comments. If you have some specific topics or something that you'd like to work on, let me know. I'll be making more videos soon. And yeah, if you want to see some other of my videos, click here. Click.